Whenever we're dealing with multiple different random variables, we might want to think about how those random variables behave individually or jointly, just as the random variables themselves. However, we also might want to consider some combinations of these random variables or functions that take in multiple random variables and combine them in some way. And if we want to start trying to think about these combinations of random variables or functions of multiple random variables, we're going to want to know how to summarize the behavior of these random variables. And so, for instance, talk about their expected value or their variances. So it's very common when dealing with multiple random variables to combine them together, and understanding the behavior of these functions of many different variables requires our joint distribution. So let's think of a motivating example here to discuss what we're thinking about in general. Suppose that we have a freelance worker and they're interested in understanding or forecasting their total income over some period of time into the future. Now, their total income can be broken down into two main important variables. So X would represent the number of contracts that they actually take on, and Y is going to represent the contract value or the average contract value. And so then the total income that they actually earn over the period of time is going to be dependent on these two random quantities, right? Both an X and Y are random quantities, and we could think about those individually together. However, taken together, if we multiply them, then we have that the total income is going to be X times Y. And so instead of us just thinking about studying how many contracts or the average value, which there might be a reason to do, if what we're actually interested in is the total income in some period of time, then what we want to do is we want to combine X and Y together through multiplication. And so then, for instance, it would be very reasonable for this freelancer to ask, well, what is the expected total income over some period of time? Which is to say, what's the expected value of X times Y? Or what is the variance of the total income over time? What is the variance of X times Y? And so to address these questions, we need some way of talking about the expected values or the variances of functions that take in multiple random variables. And so when we're thinking about these multivariate transformations, we need to think about how we can actually summarize those random variables. So what are we thinking about with respect to expectations of these multivariate functions? Suppose that X and Y are going to be random variables. We know they're joint probability mass functions. That's P of X and Y. Moreover, suppose that what we're concerned with is some third random variable, which is W, and W is going to be a function of X and Y. So we take something, we plug in both X and Y into it, and that's going to give us a response for W. Now, importantly, in our case here, W has to output a single value, not some vector of values. There are going to be ways of dealing with vectors of values, but that's not what we're going to be thinking about with this lesson here. Instead, we want to think about summaries that take in multiple values and output one single value. So, for instance, X times Y is a variable that would work in this way. Now, the distribution of W is going to be dictated by the joint distribution of X and Y. If you want to know what is the probability that W takes on some value, then what you need to do is you need to back solve to that using the joint distribution of X and Y. But more concretely here, if we think about the expected value, then the expected value is actually going to be able to be defined in a way that's very similar to any other expected value, except using this joint distribution. So the expected value of W, which is the expected value of this function of X and Y, is going to be the summation over all of our possible combinations of values. So that's the summation over every value for X and every value for Y of that function times by our joint probability mass function. Right? So it's the summation over everything times by the joint PMF. Essentially, what we've done here is we've taken the definition of expectation from the marginal case or even the conditional case, and we've used the joint PMF instead. And really the thing that we have to be mindful of is that when we're using the joint PMF, because we have two variables in this case, we have to sum over all of those combinations of variables. So it's not just the summation over one of our indices, it's the summation over both of them simultaneously. Okay, so by summing over both variables, we can then generalize this to the case of our expected value. Now, if we want the variance, right, so we want the variance of W or the variance of G of X and Y, then what we can do now that we know how to take expected values of functions of multiple variables, we can define the variance in exactly the same way, right? So we take g of x, y, minus its mean. We square that, and then we want the expected value of all of that, right? So this is our standard variance definition, but knowing that if we want to take those expected values, we need to be thinking about this joint expectation up here, okay? And we can simplify this down. It's a lot easier to compute the expected value of g of x and y squared minus the expected value of g of x and y, all of that squared, typically, okay? And so in this case, right, we're thinking about we can take these multivariate functions, we can find their expected values using that joint distribution, as long as we make sure to sum over all of our combinations of variables here. So as our first example, we'll take a joint PMF of x and y. Right, that's going to be x plus y over 21. X can be any value between 1 and 3. Y is a value between 1 and 2. And first, what is the expected value of x times by y? Okay, and so in this case, right, if we want the expected value of x times y, what we need to do is we need to sum over all of our values, right? And so we're going to be summing over the values from x being 1 up to 3. We're going to sum over the values of y from 1 up to 2. Okay, and then what we do is we take our function, so that's x times by y, times by the joint probability mass function. So that's x plus y, divide that by 21. Okay, and so there's going to be a total of 6 terms here, and so we'll write these out, right? But these types of calculations can certainly get a little bit tedious to do by hand. So x starts off being a value of 1, y is going to be a value of 1, and so then we have 1 times 1, 1 plus 1 over 21. And then we have x being 1, y is 2, 1 plus 2 over 21, right? Going on now, we have x being 2, y is 1, 2 plus 1 over 21, right? Then we're going to have both of them being 2. Then we have x that is now 3, so that's 3 with y being 1. And then finally, x is 3 and y is 2. Okay, and so conceptually, this is not challenging. It's not different from doing this in the marginal case. However, it can be a little bit tedious, right? There are 6 terms here based on this joint distribution, and that's because there are 6 combinations that x and y can take on together. And so to find this expected value here, we need to work through sort of all of this, right? But if you plug that into a calculator or whatever, then what you'd find is the expected value of x times by y. Right? And so working this out, right, we can write out that full summation there again. That's 1 over 21 times by that sum that we talked about there, which is 72 over 21, or 24 over 7. That gives us about 3.43. Okay? And so conceptually, it's the same as calculating a marginal expectation. Practically, it's a little bit more involved. Now, what about the expected value of xy squared? And so here, again, without writing out the whole term once more, if we want the expected value of xy squared, right, then what we do is we sum over all of the values for x, we sum over all of the values for y, and then we take xy squared times by our probability mass function here. So that's x plus y over 21. Right, again, we're going to have those 6 values to plug into here, but once we've done all of those, work through that summation, that's going to give us our response here as well. Okay. So once again, stepping through, right, this looks almost identical to what we were doing on the previous slide. The difference is we're squaring these values because we want x times y squared, right? And so by squaring everything, what we find is that that's going to be 306 over 21, which is 102 over 7, or about 14.571. Okay. So again, computing the expected value here, not a lot different than computing the expected value for a marginal. We're using the joint here, requires summations over more terms. Now, what about the variance of xy? So the variance of xy, right, is the expected value of xy squared minus the expected value of xy squared. And so we worked out both of these expectations in parts A and B, right? And so then we take the one that we have from B, we subtract off the one that we have from A squared, and that's going to give us our variance of x times y. So because we've already calculated those expectations, it's not too challenging here, right? We plug into our formula there. That's 102 over 7 minus 24 over 7, which gives us 138 over 49, or 2.816. Okay, and so here we have a joint function of multiple variables, we find the expected value and the variance of this by considering the relationship to the joint distribution. Take a look at a sort of more practical problem in this case. We have a hospital emergency department, and they're tracking two different random variables during a 1-hour period. So X is the number of patients that are leaving the emergency department without ever being seen, and Y is the average wait time for a discharged patient. Okay, so the joint PMF of X and Y is going to be given to us by this expression here. So that's X times Y over 30, where X is a value 1, 2, or 3, and Y is a value 1, 1.5, or 2.5. Okay, so we have our joint information here. We could consider both of these variables individually, right? We could think about working out any of that information. But what we have is that the provincial health authority is thinking about issuing this penalty cost, which we're calling C, based on these two factors. And C is going to be set to be $500 if either X is greater than 2 or Y is greater than or equal to 1.5. What we want to know is what is the expected penalty cost for this hospital? And so we have this sort of function that is going to be 500 if either of these conditions is met, or it's going to be 0 otherwise, and we want the expected value of C. And so what we can do is we can introduce some notation here. And so I'll introduce the notation, this I function here, and I'll say it's I, X greater than 2, Y greater than or equal to 1.5. And all this is this is going to tell us a value of 1 if either of those conditions is met, or 0 if they're not met. Okay? And so, for instance, if you plugged in X is equal to 3, then you would have this being a 1. If you plugged in Y equals 2.5, you would have this being a 1. But if X and Y are both 1, then this would be equal to 0. And then the cost is therefore going to be equal to 500 times by this function I over here, right? So C is 500 times by this function here, right? I of X and Y. Okay, and so ultimately what we want to do here is we want to find the expected value of a multivariate transformation here. And so we can sort of think about, well, what is this expected value for C here? Okay, the expected value for C is going to be the expected value for 500 times by this indicator function that we just defined. Okay, now this 500 is a constant, and so that's 500 times by the expected value of this indicator function. Okay. And so how can we work out this expectation here? Right, well, this expected value of this indicator function, right, if we actually wanted to talk about what that is, then by definition, this is going to be the sum over all of our values for X, the sum over all of our values for Y, and then it's the indicator function times by our joint probability mass function here. Okay. And so now let's think about what's actually happening with this summation, right? The indicator function is always either 0 or 1, right? It's 1 if those conditions are met, and it's 0 otherwise. And so what we're going to do is if we actually think about trying to simplify down this summation here, we're going to have 0 everywhere that that condition is not met, and we're going to have 1 everywhere that the condition is met. And so in other words, what we're going to be doing is we're going to just be adding up our joint probabilities across all of the values where that condition is met. And so that's going to be a value of, say, X being 1 and Y being 1.5 or 2.5. X could be 2 and Y could be 1.5 or 2.5, or X can be 3 and Y can be any of the 3 values there, right? And so then we're going to have 2 values where X is 1, 2 values where X is 2, and 3 values where X is 3, all added together. So we need to add up those 7 probabilities, and that's going to give us the expectation here. Okay, so let's work through all of this and sort of work that out to the end. What is the expected penalty cost for the hospital? Well, we can indicate or draw in our indicator function here, right? It's taking a value of 1 if the condition is met and 0 otherwise. And so the cost is 500 times by this indicator function, and so that's 500 times the expected value of it. Right? And so working out its expected value, what we want to do is we want to sum over all of those combinations, right? The indicator function times by the joint probability. But all we're doing here is it's going to be 0 anywhere the condition's not met, and it's 1 everywhere that it is met. And so we're only left with the places that it's met. So that's the probability of 1 and 1.5, 1 and 2.5, 2 and 1.5, 2 and 2.5, 3 and 1, 3 and 1.5, and 3 and 2.5. And so then if we add up all of those probabilities, all just coming out of our joint distribution here, we find that that's going to give us 27 over 30. And so then with that 27 over 30, we can turn back to the expected value of C. It's going to be 500 times 27 over 30. And so the expected value of this cost is going to be 450 to the hospital based on their current standards of X and Y. Right, so a little bit more involved in coming up with this, but these types of things are going to be the ways that we might think about summarizing random variables in practice. Now, importantly for us to think about is what happens if we have independence. And independence can greatly simplify some of these calculations, specifically when we have separable functions. And so what do we mean by that? Well, let's suppose that g of x and y can be written as the product of two terms. One of them only depends on x, the other one only depends on y. So that is, we could write g of x of y is g1 of x times by g2 of y. And if we can do that, things get a lot nicer if we're going to have independence. And so what are some examples where this would work? Well, if we take x times y, right, then x times y we can separate into simply x as our first function here, and then y as our second function. And so that's going to work out totally well for us. As another example here, if we have x squared divided by y, right, well then if we take our first function to be x squared, that only depends on x. If we take our second function to be 1 over y, then multiplying those two together give us our function there, and so that works out as well. A third example here, we can take e to the power of x plus y. Right, and how does this work out? Well, if we take the first one to be e to the x, and the second one to be e to the y, multiplying those two together gives us e to the power of x plus y. Okay, and so all of these would be examples where we can actually separate out the function to something that depends only on x and something that depends only on y. If we then suppose that x and y are independent random variables, then the expected value of g of x and y is the expected value of g1 of x times by the expected value of g2 of y. Okay, so we can separate out this into just marginal expectations, right? Because we are dealing with just marginal expectations, that does not need us to consider the joint distribution at all, which is going to be very handy in many cases because summing over the joint distribution is going to be a lot more involved than summing over marginal distributions, generally speaking. So if expected value of, or if x and y are independent of each other, then for instance, the expected value of x times y is the expected value of x times the expected value of y. Now, this is all following because if we have independence, then our joint distribution can be written as the product of our marginal distributions. And so if we just take our defining relationship that we had found before, you'll be able to find that that can all be separated out. So as an example here, we'll take x and y to be independent random variables with probability mass functions given to us here, as p of x is going to be 25% chance that it's 1, 50% chance that it's 2, 25% chance that it's 3. And for y, there's going to be a 50% chance that it's either 100 or 200. And first, what we want to do is we want to find the expected value of x times y. So the expected value of x times y, normally we would require our joint probability function, but because we have independence, this is going to be the expected value of x times by the expected value of y. And so then we can work out what is the expected value of x, and that's going to be 1 times 0.25 plus 2 times by 0.5 plus 3 times by 0.25. Okay, and so then we have 0.25 plus 1 plus 0.75, so that is 2 here. Okay, what's the expected value of y? Well, the expected value of y is going to be 100 times 0.5 plus 200 times by 0.5, which is going to give us 150, rather. Okay. And so then the expected value of x times y is going to be 150 times by 2, which is 300. Okay. So in this case, we can simplify everything down because we know these are independent random variables. If we didn't, we would need to know what is their joint probability here. Okay, so we have the expected value of x is 2, we have the expected value of y is 150, and thus the expected value of x times y has to be 300. Now, what is the variance of x times y? Well, in this case, right, the variance of xy is going to be the expected value of x times y squared minus the expected value of x times y, squaring this piece here. Okay. But this first term, right, what we can do is we can write that as the expected value of, say, x squared times by y squared, right? And that is, because of independence, just the expected value of x squared times by the expected value of y squared. Okay. And then for this other term over here, well, we've already found that this right here has to be equal to the expected value of x times the expected value of y, and so then we can simply square that whole thing. Okay, and so the variance of x times y is going to be given to us by this. We already know what the expected value of x is, we know what the expected value of y is, and so then we can find the expected value of x squared and the expected value of y squared and plug in there, right? So the expected value of x squared is 1 squared times 0.25 plus 2 squared times by 0.5 plus 3 squared times by 0.25, right? And similarly, the expected value of y squared is going to be 100 squared times 0.5 plus 200 squared times by 0.5, right? We plug all of those in together, we multiply these two things, and then we subtract off our response from 1. Okay, so that's going to be subtracting off our 300 squared. And so working this through, right, expected value of xy squared is expected value of x squared times y squared, which is the expected value of x squared times the expected value of y squared. So from our marginal probabilities, we get a 4.5 and 25,000 for those two expectations here. And so the variance is going to be the product of those two minus 300 squared, which gives us 22,500 in total. So functions of multiple random variables are often going to be summarized using these multivariate transformations. We can do this both in expectation and in variance, finding the expected value and the variance of these summaries. And these expectations are all going to be calculated based on the joint distribution. Generally speaking, we need the full joint distribution to calculate these out. However, if we have independence, and if the functions that we're thinking about can be separated into functions that only depend on x and those that only depend on y, then we can end up simplifying down the calculations quite a lot through that independence assumption. If we don't have that independence assumption, we go back to the joint distribution, and mechanically, it's not much more difficult than working through, say, a marginal or a conditional expectation. The difficulty comes because often there's going to be many more terms that we need to keep track of, and so it becomes more tedious, although not particularly more difficult.